First, it's the end of the day, so I will try and speak fast and maybe be entertaining. Second, it's a real pleasure to be here, and I wanted to thank you for the invitation. I'm at the moment at DARPA, but traveling internationally from DARPA is very difficult, and so I am not here officially. I'm visiting friends, but there is a lot of friends here, so it is absolutely fine. And what I want to, another thing that I was thinking, every time I come at the fields, this is one of the places that Jerry Marsden built, and many of us, certainly me, we say this with Igor sometimes, we have things and like we wish Jerry was around to ask him or tell him about something, so it's a pleasure to remember him. I wish he were with us. And I want to say, if I have time and speak quickly, I want to say three things. By the way, some of the many good people are here. Tom Bertelan, who used to be my student and postdoc and now works separately, has a poster and he's here. And then among the many friends, some of the things I'm going to say involve Eric. And this guy is my son, who is finishing a PhD in applied math, working with other people, but during COVID, he stayed with us at the house, and so I kind of got him to do some calculations that I... So you may remember in Latin history, there was Cato the Elder, and every time he finished his talks by saying, we must destroy Carthage. And these days I start my talks by saying, here is some old stuff that we used to be doing a long time ago on using machine learning in the early 90s or late 80s to do dynamical systems, but while if in some sense this is an advertisement of old stuff of mine, I do bring it up because I included a couple of slides that have to do with a discussion that had to do with discrete versus continuous Koopman calculations this morning. So this is a very old paper from 1992. It has a decidedly non-machine learning title, Discrete versus Continuous Time Nonlinear Signal Processing of Copper Electrodissolution Data. It is in a decidedly non-machine learning journal called Chemical Engineering Communications, and it has experiments that were done in the lab of Jack Hudson, who is a friend and now he has passed away. And basically what we had is that we had a lot of time series of what happens if you take a piece of metal, in this case copper, you put it in an acid, in this case hydrochloric acid, there is a battery and a reference electrode, and as you change the potential between the metal and the reference electrode, you see that value up there, 0.67, 0.6768, then you get lots of time series. And if you do time delay reconstruction, you get steady states, limit cycles, period doublings, period quadruplings. And the problem at the time is we can only measure one thing. This is what we get. How do we get a model so that we can understand the bifurcations? The question at the time was understanding the bifurcations of this problem. So what we did is to look at numerical analysis. So this is a transcription of a fourth order Runge-Kutta. And then what we did is that we constructed a recurrent residual network, which would look at discrete time data, yn and yn plus 1, and which had a very particular architecture. If you look at it, I'll try to take you through it. It is absolutely Runge-Kutta, so we didn't invent anything. You take a data point, you pass it through a multi-layer perceptron, you get the result, like Runge-Kutta does, take the result, multiply it by a given fixed small number, add it to the initial condition, pass it through a multi-layer perceptron, the same one. You do this 4 times, and then at the end, the answer is not yn plus 1 as a function of yn, but the correction, the residual, between yn plus 1 and yn, which is 1/6 k1 and 2k2 and 2k3. My point is the following. Training this neural network will give you a multi-layer perceptron that approximates f. So this is not a way of learning the time one map. It is a way to learn the right-hand side of to approximate the right-hand side of the differential equation. But the point that I would like to make is that, maybe if you want motivated by this, is that I very much believe that many of the successful architectures that come up in machine learning in recent years, and not so recent, really, if you look at the old traditional numerical algorithms that we know and love, then you will find them there. So a Runge-Kutta by itself, not our little architecture, but a Runge-Kutta by itself is a recurrent residual process. And it's interesting that when residual networks were proposed, it was a 2015 paper, Kaiming Hayes now at MIT. If you look at it, you recognize forward Euler. This is well established by now. What you learn is not a function of y0, but this is f of x. This is f of x times a small number added to y0, and that gives you yt. You're really learning the integrand, not the result of the integration. And another thing that is interesting is that you may remember we had only a single time series, but it was a chaotic dynamical system. We needed more variables. Where did these variables come from? I was talking with Alan today. This is a paper from 1991 by a guy called Mark Kramer, who was a professor of chemical engineering at MIT. He did not get tenure, but he did fine in life afterwards. And this paper we looked, it said 4,000 citations. I don't know how many it has now. And this is my first reference for autoencoders. He called them nonlinear principal components, and the paper was 1991. If you know a previous publication of this, please do tell me. I'd like to know. So what we did is that we used windows of the time series to find three nonlinear principal components, and then we used this recurrent ResNet based on Runge-Kutta to learn the right-hand side of an equation which, when integrated by Runge-Kutta, would pass by the time series of the experiment. And now that we had a right-hand side, depending on parameters, we could do the bifurcation diagram. You know, there was a Hopf bifurcation and the period doublings, and there is attractors and phase portraits. But as I said, I'm saying this because there is a little twist. When in this problem, and that's another reason we did it this way, we did not learn the time one map. We learned the right-hand side of the differential equation. Why? It turns out that if you're interested in a bifurcation study, when you have limit cycles in continuous systems that have translational invariance, discrete systems don't have translational invariance in time, and therefore what you get is invariant circles. And those of you that have spent their times playing, some part of your life playing with resonances and frequency lockings in invariant circles would probably know that while, for example, the period of a limit cycle is a smooth function of a parameter, the rotation number on an invariant circle is a devil's staircase. It's a horrible object. And I was thinking, as both Igor and we're speaking today, when you use pairs to do the calculations of Koopman spectra, this issue of translational invariance versus non-translational invariance should show somewhere up in there. So I asked Igor in the corridor in the break, and he said that if we look at the right paper, so you can say it either now or at the end, but there is a place in which this issue is discussed. But what I do want to show you here, just to kind of as a visual plot of the fact that are horrible, the things that are horrible with discrete versus continuous problems, this doesn't have to do with accuracy. You can have an extremely wonderful short time fit. The long-term attractors are wrong, and the bifurcations of the long-term attractors are wrong. This is a stable invariant circle and an unstable invariant circle, and as you change the parameter, they will come close to each other, they will collide and disappear in a saddle node of limit cycles for the continuous time problem. Well, for the discrete time problem, this doesn't happen. There will exist an entire interval of parameter space over which these guys will wrinkle, will lock, stable and unstable manifolds will cross. Eventually you will lose them, but the bifurcation is not a crisp single parameter bifurcation. So this is one of the things that I kind of have thought over a long time, reconciliation. If somebody gives you a time one map, how can you figure if this time one map comes from a differential equation or it is a generic time one map that has all of these generic features in its bifurcations? So you can think of these as pathologies of neural networks. And one more little thing from back then, from the ancient history. This is, if you look at the formula up at the top, you will recognize Crank-Nicholson. So the idea was take the numerical analysis algorithms that you know and then figure out what are the corresponding neural network architectures. And this is something that's relatively recent, and here's Tom Bertelen again, that I learned from Aiking Zhu, who is actually now he's in Singapore, like Shanshao, he works with you. And bear with me, this is another kind of interesting relation in my mind between numerical analysis and neural network architectures. Okay, so typically, if we have a differential equation, we can either have the true solution or a numerical solution. And usually we look at the difference of the true and the numerical solution, and this is forward error analysis. But if you remember, what we did before is that we tried to find an equation which, when integrated by Runge-Kutta, would pass by the true solution. So we did not actually learn the right-hand side of the equation. We learned an approximation of the right-hand side of the equation. And how was this approximation affected? It was affected by finding something called an inverse modified differential equation. That's an IMD up there. It's an equation whose Runge-Kutta passes from the true solution. And now, if the numerical integrator is good, then the true ODE and what we find are close to each other. So we don't look at the differences between the solutions. What we look is at the differences between, if you allow me to use the word, the generators of the solutions. And most of the neural network schemes that are learning right-hand sides of equations from data, they're really learning what is called here an inverse modified differential equation. This also has the rather horrible rubric of inverse backward error analysis, which sounds really bad. Inverse backward is not very nice. But again, this is something that has been studied traditionally. And the last thing that I'm going to show, which is not the old, but it is new, and it's the subject of the first program that I ran at DARPA, I showed you this picture from 1992, where the black is hardwired, it's Runge-Kutta, the red is unknown, and it's learned from the data, and this is a problem in which you have data and the integrator, and you learn the model. And this is a different version and a different use of the same idea. Here you again have the data, you have the equation, but you are teaching the neural network to learn the algorithm for solving the problem. So it is the same architecture, but by changing what you know and what you do not know, in this case you have the data, you have the equation, and then you can try and use meta-learning, various types of optimization in order to learn the algorithm based on optimization. I had some work on learning algorithms via optimization for a long time. If you think about it, an algorithm is a sequential decision process. An iterative algorithm is a feedback loop. You do a number of decisions, and then you feed the result up to the initial condition to update it. So if you give a cost to everything you do, then finding an optimal algorithm becomes an optimal control problem. And so, as I said, there is also 2 years ago, there were 2 papers back to back from Google DeepMind, where they used reinforcement learning to find matrix multiplication algorithms and sorting algorithms. So it's an interesting thought to try and find optimal algorithms somehow via optimization. Okay, now this is one of the 42 already, okay. So this is one of the 2 real things. All of this is somehow old stuff that I told you up to now. It's a paper in which Eric Bolt also is a co-author. We've been talking about it for some time, and it has a really pretentious title, Learning What to Learn. What really it is looking at common and sensor-specific information across multiple sensors with some thoughts about causality. That is too many things. What it really says is the following. If I am going to learn a relation between X and Y, then yes, we have a lot of tools of learning a function, but first we must decide what is X and what is Y, what is a function of what. And so the idea is that we need to find what are the things that correlate together. You can think of it as a hymn or as applications of nonlinear versions of canonical correlation analysis. So the idea is, let's say that I have some stream of information that has data from X and some 2 other processes, and then you have another stream that has information from Y and 2 other processes all mixed together. How can we figure out that X correlates with Y, separate the Z1 and Z2, if you want, disentangle them from the X and the W1, W2, so that then we can go on and learn the relation, the observer, if you want, between X and Y. And what I'm going to talk about first, there's one little thing that we did with my son also, is something that was done by 2 postdocs of Rafi Koifman at the time, Ronen Talmon, who now is at the Technion, and Roy Lederman, who is now a professor in statistics at Yale. What they did is that they bought 3, this is an experiment by mathematicians, they bought 3 little robots and 2 cameras, and the robots are spinning around, they're dancing. Also, one of them is Yoda, one of them is a bunny, but the bulldog was because they were at Yale. And what they did is that they got the two cameras to take pictures of these things that were spinning. They were spinning with irrational ratios, okay? And the important thing is that every time that camera number one sees this, then camera number two will see the bulldog, but it will not see the same bulldog, it will see another view of the same bulldog, okay? So they see the same process, but they don't see the same thing. And they did something very interesting that I am not gonna do justice to. I'm just telling you the process. I is the data point, SI, it's what camera one, do you see the superscript one, observes? So you look at all the pictures observed by camera one and look at their differences and you put them in a matrix, in a kernel matrix. You look at all the observations over all the data points that are done by camera two and you multiply these two matrices. It doesn't matter if you multiply them K1, K2 or K2, K1. And then what you do is that you go and find the eigenfunctions of this composite kernel. These eigenfunctions have something to do with what is common between the two cameras. Let me kind of explain in a hand-waving way what is really happening. Let's take one picture from the first camera. And then this is the corresponding picture at the same moment in time from the second camera. Then you search all through the movies and try and find all the pictures that look like this from camera one. Then you look at what are the pictures that were observed at the same moments in camera two. Well, since the bulldog looks like this in the pictures from camera one, it has to look the same in camera two. But because the bunny is a separate process, every time that this looks like this, the bunny could be anything. And so really what happens in a way is that doing this process averages over all possible spins of the bunny, and that, it's not exactly true, it doesn't average, but that's the main idea. So this process that looks at all pictures from camera one and all pictures of camera two, it will look at what corresponds to the same thing over both the observations, and then there's the things from here and here that will average out. Average out is not the right expression, but this is the main idea. You look at things observed at the same moment, and then you try and figure what looked the same and what didn't look the same. This is an easy case, what we tend to call clean pixels, where a pixel from this camera is either bulldog or Yoda, but you can think of, let's say, these being glass robots that are put in a way so that you're seeing a combination of the two. So it's not that you can do only the clean pixels, you can do messy, dirty pixels, as we call them, where what you see may be a combination of the common and the uncommon things. I understand that I am not explaining, but the basic idea is that you can create an eigenproblem whose solution will first give you the dimensionality of how much is common, and then it will give you an intrinsic space that parameterizes what is common. And so finally, what does that have to do with dynamical systems? This is my little example. This is my bulldog. It is a set of two differential equations that are nonlinear and have a limit cycle. And then this is my Yoda and my bunny. There is a quasi-periodic system that is periodically forced, and then there is the Lorentz equations. And basically, the situation is the following. We have a situation in which sensor one sees mixtures of time series from system 2, which is common, and system 1, and sensor 2 sees mixture of time series from the Lorentz and system 2. And there's one more little important thing to say. They see time series from the common system, but not the same time series from the common system. Look, the sensor 1 sees some green things from here, some yellow things from here. The other one sees some blue things from here and some yellow things, but look, the yellow things above are theta sub A and the yellow things below are theta sub B. So these are supposed to be generic observations of the system too. If you analyze these data with the process that I described, which is summarized again here, then you find that the common stuff is two-dimensional. There is a limit cycle of the yellow system, and you get the number of eigenvalues that correspond to that, and then you also get an eigenspace in which you can embed the common stuff. And now here is the one interesting thing. Once you found that something is two-dimensional, and you found this is alternative diffusion maps, and you found coordinates for this intrinsic space, then what you do is that you take what each pixel did and plot it in this intrinsic common space. If the pixel is a pixel that comes from the bulldog, i.e., if it's something that is part of the common space, then its behavior is smooth. You kind of see that the behavior looks nice in terms of the color scale. But if the pixel corresponds to Yoda, then as we follow the bulldog, Yoda could be anything. And so the Dirichlet energy of the function of the uncommon pixel projected on the common variables looks like hell. And this is the way by which we can decide which part of the data corresponds to the common and which parts of the data corresponds to the uncommon. Once we figure out, so this is the little punchline of this part of the talk. Once we figure out what from the first probe camera is common with what from the second camera, oh, now we can do anything we want to learn the function. We can use k nearest neighbors, we can use diffusion maps and geometric harmonics, we can use Gaussian processes, we can use neural networks to learn the function between what was observed by camera 1 and the common thing that was observed by camera 2. Let me say there was a word causality in the talk, somewhere hidden in the long title. Remember, I'm trying to find things common between two cameras. Well, if camera 1 is the present and camera 2 is the future, then what is common between the present and the future is the evolution of the system. So if we use this approach to look at delayed measurements, then we can learn the evolution for the problem. We can get from the evolution of one variable, we can get the evolution of the other variable. And let me, okay, and this is the thing that we did with my son that I was telling you. This is exactly the same process, but instead of doing it spectrally, it is done through an ad hoc neural network architecture that we kind of thought one evening during COVID, in which we call, we have to come up with a word, conformal autoencoders. Let me explain. There is one interesting idea in this, but I think it's cute. So this is camera 1, it sees 5 things. This is camera 2, it sees 5 different things, but 2 are common. So this is an autoencoder that does not do any reduction. It just rearranges the space. It deforms the latent space so that this goes, these, if you want, mixed variables go to 5 other variables. They are enough to reproduce everything, so no information is lost. But now in this rearranged latent space, 2 of the variables from camera 1 are the same as 2 of the variables from camera 2. And here is the one interesting thing. The 3 up here and the 3 down here are, by construction, orthogonal, conformal to the things that are common. So this is an autoencoder that does not reduce things, but rearranges things to the things that are common and the things that are uncommon between the 2 different streams. Then, as I said before, we can kind of go and try and learn, based on what we see on this camera, what will the other camera see. Let me point one more thing. I think that's the last thing I want to point from here, that if you want, this is what is observable from the first camera. This is not observable, it's an orthogonal space. There exists a reasonably systematic way that if we get something from camera 1, we can see which combination of the camera 2 variables is observable, and then we can also sample nicely the level set of all possible things that camera 2 sees that are consistent with what was observed in camera 1. So we can find what is common, and then we can also find the level set of all of these uncommon things that could have been observed along with the common. I understand that in English it sounds a little bit funny as I'm saying it, so let me kind of give you a reasonable example of this. Yeah, and I was told that 5 is really like I will get killed if I go beyond 5.
This is a little slow.
And this is slow? No, you didn't tell me that, so it doesn't count. So here is a real good use of this. This is a set of differential equations, and it comes from some enzyme standard book problem. I got it from Stas Schwarzman, my ex-student and colleague, and this problem has 3 parameters, but trust me, in some corner of parameter space, there's only one combination of the parameters that matters, one effective parameter, and the rest don't matter. Well, if we take an initial condition, and then we integrate the system for a short time using all possible perturbations in these 3 parameters, we are going to get a whole lot of solutions. But if we analyze these solutions, if every solution is a data point and we analyze them and find their diffusion map components, we will find that there exists only really one non-trivial diffusion map component, because yes, there is 3 parameter family of perturbations, but there is only a 1 parameter family of responses. So here what we're trying to do is that we're trying to find what is common between the parameters of the problem, that's the inputs, and the outputs. And because we found that only one output is important, the cardinality of the outputs is 1, in our conformal autoencoder, we rearrange the parameter space non-linearly so that one of these corresponds to the output and the other 2 are orthogonal to it. So if you want, we find the combination of parameters that affect the output. Think of them as a sort of data-driven dimensionless parameters, and the combinations of the inputs that don't affect the output. Again, the most important thing is, you can see down here, it says d nu 1, d nu I, d nu j 0. The important thing is the conformality between the things that matter and the things that do not matter. So this is a way of, if you want, doing some sort of practical data-driven, certainly doing parameter reduction, but in a way doing a sort of data-driven dimensional analysis in parameter space. And I think that is more or less what I wanted to tell you. The other problem that I will not talk about, but I am kind of fond of, is the following. So think of this as a teaser. You learn an operator as a black box. You learn it by doing neural operators, you learn it by doing DeepONet, or you learn it by doing Fourier neural operators or whatever. So you have an operator in a black box. And now you're going to solve this problem for some new initial or boundary conditions. If the operator is hidden in a black box, how do you know what the good boundary conditions are going to be? How do you know when a problem learned as a black box is well posed? So it is an interesting thought to consider if an equation is hidden in a black box, whether it comes from multi-scale calculations, whether equation-free calculations, whether it comes from learning. Usually when you have an equation, you want to see how many boundary conditions it has. You look at what the highest derivative is, for example, or you have to say, is it a parabolic or elliptic equation? You have some tests to do based on the formula to decide some things about the nature equation or the nature of the equation that are important in solving it. But if the equation is in a black box, what are the numerical experiments you should do to decide the qualitative nature of the equation? This came up a lot 20 years ago when we were doing multi-scale calculations. You have a closure, but you want to know some things about the nature of the closure, and it comes up again now. And Alan told me that you might call this an operator tomography. We call this, how do you figure out the nature of the unavailable equation? There is nothing particularly difficult, but it puts up a lot of interesting questions, like how do you figure out if a black box equation is a conservation law? What experiment should you do? Okay, that's it. Thank you.